Welcome to this month's WCAI webinar entitled Wireless Technologies and Architectures for Small Cell Backhaul. I am Chris Horne of LBA Group and the moderator for today's exciting presentation. Today's presentation on small cells and backhaul will last for 45 minutes with a 15-minute Q&A session at the end. You may submit questions electronically during the presentation, and I will forward those to the appropriate speaker. A few years ago, some operators underestimated the requirements for 3G macro-cell backhaul to meet data traffic demands and are playing catch-up to meet capacity density needs for LTE. Traditionally, operators enhance their networks with macrocells, but the future will be enhancing capacity with microcells and metrocells. Although Wi-Fi offload is one alternative for operators, growing demands for carrier-grade wireless services in small cell hot zones make cost-effective backhaul more important and challenging than ever before. This webinar will provide an overview of the new microcell network architectures and new technology options for backhaul. Our first speaker is Caroline Gabriel. Caroline co-founded Rethink Technology Research in 2002 to focus on emerging mobile technologies and their impact on operator business models. She has been analyzing and reporting in the high-tech industry since 1986 and has a huge wealth of experience in technology trends and how they impact business models. Following Caroline will be Greg Friesen. Greg is the Vice President of Product Management at DragonWave, responsible for global product management and responsibilities. Greg has 13 years experience in senior product management roles, network design, planning, and engineering at a number of communication firms. His experience ranges from operations and CapEx modeling to network architecture design to site and link engineering. And without further ado, I'd like to introduce Caroline Gabriel.
Hello everybody, welcome to the webinar. Very happy to be talking today about the context for the changes in backhaul that we're going to see over the coming years, and then I'll be handing over to DragonWave to give a lot more detail on exactly how that's going to pan out. I'd like to point out that having co-founded Rethink Research about 10 years ago, we focus very much on operators and what they're deploying in terms of technology and how that's supporting their business models. So a lot of what I say in my kind of warm-up to Greg will be based on recent surveys that we've done in the mobile community. We're also really pleased lately to have combined our research efforts with those of another very innovative 4G analyst firm, Maravedis, and they're particularly specialised in backhaul. So we're drawing here on two sets of research which we hope will be complementary and give a few insights to set the scene for Greg's presentation. First, before we can talk about backhaul, we obviously have to outline some of the changes that are taking place in the access network, which of course will drive the new approach to what operators are deploying in terms of backhaul over the coming years. Based on a survey of about 100 mobile operators that we did at the end of last year, we can see the rapidly changing priorities that they're looking at as they build out particularly their LTE access networks, although this does also apply to HSPA+. And looking forward to LTE Advanced, which many carriers believe they will already be starting to deploy in 2015 or even in some cases earlier. Among those 100 operators, the top priorities, objectives for LTE and LTE Advanced that they want to achieve over the next 3 years only is to reduce their cost of delivery by 35%, to reduce the power consumption in their networks by 85%, and to boost their average data rates by at least 200%, much higher in many cases. And that's not even talking about the increases in overall capacity that they're targeting. None of these are achievable even given an upgrade to LTE without a whole different architecture in the network. And the key methods, the top 4 methods that were identified by the same survey as the key enablers for their objectives are the use of far smaller cells in greater numbers, self-organizing network techniques, which are essential to enable the small cells to operate together in any effective way without interference. New approaches to network planning, which will both be easier and more automated and will take account of multi-layered networks, such as the one that you see in the diagram, where there are several small picocells within a macro cell, providing a layer of capacity for an area of particular demand. And advanced traffic management to ensure that the appropriate subscribers and applications are sent to the right part of the network for their requirements. All of this requires a dramatic rethink in backhaul. You can see just from this very simplified diagram how many elements there are operating in different spectrum bands, often with different air interfaces, different layers, different power levels. That is a challenge for the access network, but it's also a huge challenge to make sure that each of those elements is backhauled effectively to support the required data rates, but also without wasting a lot of capacity. Just to reinforce that, again, this is all about small cells. Greg will tell us a lot more about the specific backhaul implications of that. But to give some context, also based on our surveys of operators and a more recent one that we've done just in the last few months, we can see how the installed base of base stations that carriers are using is changing dramatically. So by 2015, you can see the orange bar, which is the compact base stations, and these are very small picocells ranging into the outdoor metro cells, which are we define as fully integrated cells that have are based on a single system on chip and usually have backhaul also integrated. Of course, they're small and relatively low cost, so you'd expect their numbers to be high relative to the network as a whole, but I think the graph shows you just how high the growth rate is going to be in terms of their percentage of the installed base, with a lot of that growth coming in 2013 onwards as operators get very happy about deploying in this new way. So metro cells, the most rapid growth in terms of access network investment, but the operators do almost unanimously say that one of the biggest reasons why they fear going too far into the small cell deployment is they're not entirely sure in many cases how they're going to backhaul this, both effectively in terms of delivering quality of service, but also cost effectively. So we see some new norms emerging in terms of general approaches to backhaul. I mentioned earlier the complexity of the new network. In some ways, LTE has simplified matters. Increasingly, networks are all IP, end-to-end, which makes management much easier in many ways. The base stations themselves are becoming simpler, more commoditized, they're running more standard ways. However, the topology of the network, very much more complicated, as the small diagram will probably indicate. Many types of base stations, many cells, a highly deconstructed network, and all of those elements need to be backhauled to the internet or connected to each other via various relays or mesh approaches, none of which are simple and some of which remain quite unproven. So some key elements of that. In general, cells move nearer to the ground. That creates a lot of challenges, both for access and backhaul, because they're no longer, the smaller cells at least, are no longer high up on towers. They don't necessarily have visibility to each other or to the devices. There'll be at least two network layers, and they may be in different spectrum bands. There's an increasing interest in using a high-level band, such as 2.5 or even 3.5 gigahertz, to support small cells which only need to have a short range. There's a rising use of fairly commoditized backhaul. Some operators even thinking about using DSL for their most basic metro cells, but at the other extreme, other operators thinking that they really need to invest very heavily into fiber to make this work. As I'm sure Greg will explain in detail, somewhere in the middle is probably the sweet spot in terms of cost versus performance, and increasingly that is going to be one that's filled by wireless. And some more innovative approaches coming forward. Dynamic allocation of resource is a major trend that operators are interested in, but still uncertain in terms of its effectiveness in the real world, so that your backhaul resource and other resources within the network are allocated on a sort of on-demand basis between different sites, rather than having a fixed amount allocated to each site, as tends to happen at the moment. That's to a large extent a software problem, but again, it affects the planning. It can make planning more efficient. It can also make it very much more complicated and involve some new techniques. That raises all kinds of challenges in the new backhaul thinking. These are just some key ones, which again have largely come out of the recent studies that we've done of mobile operators around the world and what their key concerns are as they look to how they're going to deploy their next network, whether that's LTE in the next 2 years or even LTE advanced in a few years' time. There are obviously high pressures on the cost per megabit second and other metrics that they're delivering. Generally, small cells and their backhaul will be very cheap per unit compared to what operators are accustomed to. But in terms of the cost per amount of data that they're delivering, they can actually become very expensive because of the huge numbers involved and the amount of management required to keep them all together. So this is a pressure. Operators are looking at how to manage so many links, how to afford them. They have the dilemma of whether, as a few operators are trying to do, they should go almost all fibre. This is prohibitively expensive in most business cases. And we see in general a shift in the CapEx budget towards backhaul as a percentage of the total. That's something that business model after business model shows to be necessary. Backhaul becomes higher capacity and you need to spend more money as a proportion on it. But it's something where we also encounter a lot of operator resistance. It's tended to be the area of the network where they've saved money, where they've kept it as cheap as possible. So there's a sort of logical shift, but operators fighting against that. So vendors are needing to not just provide a new approach to backhaul, but to make sure that that is demonstrably cost effective. The other big challenge is how to position the actual units once you're close to the ground and the cells are at a low level, perhaps on lampposts or the sides of buildings. You're obviously then into a situation where you don't have clear line of sight all the time between cells or between backhaul links. There are not just the low-level positioning, but also a lot of movement at that level, traffic going around, weather conditions, and so on. This is seen as the second biggest challenge in planning small cell backhaul. And the third one is keeping reliability and quality of service. The environmental conditions, again, they're more difficult at this level. You feel the effect of wind more, and there's therefore a huge amount of interest in the sort of dynamic approach, anything that is self-organizing, not just for the access points, but for the backhaul, so that any failure or any site that is suffering its traffic can be fairly easily sort of rerouted to a neighbouring one. So before I pass to Greg, some of the solutions to these issues which are emerging, and again I'm going to talk about these in extremely general terms because DragonWave will obviously be able to give us a lot more detail. The key is that wireless is such a rising element of the backhaul picture. You can see in the graph our Maravedis most recent report on point-to-point wireless backhaul. You can see the market as a whole forecast to grow at a very healthy rate, doubling by 2016, more than doubling. The single biggest driver, it emerges from that report, is the increasing investment into small cell backhaul and effective systems for supporting that, particularly in LTE. That is bringing in new equipment sales because people are moving into new bands, both the sub 6 gigahertz bands for non-line of sight deployments, and at the other extreme up in the millimeter wave bands. They're very high capacity, though short range capabilities. A lot of reliance, as we quickly mentioned earlier, on automation, any form of new tools that allows people to maximize the efficiency and the allocation of their resources around the network. And there's been a lot of focus on that in the access network, with, say, now increasing interest also in intelligent backhaul rather than just sort of dumb links. And the other big trend in this area towards the fully integrated unit, where the base station and the backhaul sit on the same site and in many cases are merged into the same box. That's partly a cost issue, but it's also a way that operators see that they can mix and match different interfaces, including Wi-Fi, with common backhaul, that they can save on site costs and find it easier actually to negotiate sites, which is another key obstacle to small cell networking, is getting enough sites at a reasonable price that are positioned appropriately for the business model. So we're going to see a lot of focus on vendors that can deliver a single unit, which can accomplish both the task, access and backhaul, but also without interference, either within itself or with neighbouring cells, which may of course come from a rival operator. So there are a lot of challenges here, and that's driving a lot of innovation in the market. And I think that's a good point at which to hand over to Greg, who will outline what DragonWave is doing in this area to support the new approach to backhaul.
Thank you very much, Carolyn. This is Greg Friesen, and I'm going to start our presentation now. We're going to be presenting today, kind of taking from where Carolyn left off on looking at some real deployment architectures in the small cell space. I'm not going to focus as much in this presentation on the actual economics or the DragonWave product solutions, of which we do have solutions, but I'm more going to focus on some of the real deployment architectures that those solutions can be used for. So the challenge, and I think Carolyn addressed this pretty well, but I'll just kind of recap it from the DragonWave view, is the challenge is there's a tremendous amount of user growth that's happening on the mobile side, and there's all sorts of predictions. Some say up to 18 times growth at a cell site by 2016. There's a few ways to address this. One is spectral efficiency improvement, which is expected to only address less than 5% of this new capacity that's needed. The other, which is new spectrum, which is also only expected to address a small portion of this. So that leaves a huge gap of over 70% of the capacity needed being unaddressed. So that's the first challenge. The other is operators need to improve their coverage. So there's already coverage issues that exist in networks today. If you go to any conference, busy area, I'm sure you see it already on a regular basis. I certainly do. And it gets worse with 4G spectrum, which is going to be using higher modulations and has worse propagation than 3G does. So there's going to be worse coverage as we move to new technologies unless we address the underlying architecture. And bandwidth-intensive applications are currently not well supported in indoor environments. The last is that carriers today are limited to existing tower and rooftop infrastructure, their own and others, so there's limitations in terms of where carriers can deploy today. So there's really kind of three challenges we're looking to address that the small cell architectures do. So to address the capacity gap, as I said, there's a few different ways to address it. One is additional spectrum, which, as I mentioned, only would address a small portion of the capacity gap. The other is improved RF spectrum efficiencies. That also will only go a small way to meeting the capacity requirements. Increased system load, that will help a bit, but you'll have to make trade-offs in terms of performance when doing that. And then the last, which is the one we're going to be focusing on, is increasing the number of base stations and base station locations. So essentially moving to a small cell architecture. And this is really the one that I think the industry has already accepted and looking for as the solution to the capacity requirements. But I think we all know that we're in the early stages of that, and no one's deployed this yet. So we're trying to understand what moving to small cells actually means. So some good statistics on that. Small cells obviously means you're going to be moving away from traditional tower and building top deployments to more of a street level type deployment. So if we look at some of the statistics of an urban deployment, what we're trying to do is leverage readily available infrastructure, so light poles, traffic light sides of buildings. So if we look at light poles, typically the separation in an urban core of light poles is about 24 to 30 meters, and every intersection has 4 light poles. So this becomes your new telecom mounting infrastructure. Is something that's every 24 to 30 meters with 4 of them at intersections. The distance between base stations today is carrier dependent based on their engineering rules and their business models. If we look at a 1 square mile space in an urban environment, there's approximately 34.4 miles of road and 4,200 potential microcellular candidate locations, so 4,200 traffic lights or lamp poles. When we look at it, about 7% or 320 of these are preferred candidate locations in a target zone. So, if we look at where we'd like to deploy a small cell, there's about 320 of these 4,200 in the square mile location are candidate locations that will be well suited for where we want to place our base stations. A deployable product is going to be the difference between success and a non-operational network, so something that just can't be deployed and can't meet the realities of the urban environment, which is much different than the existing telecom environment. So when we look at the backhaul options that are available for these small cells, today there is no backhaul at the lamp pole today, so we need to build something at every microcell, at every lamp pole. Fiber has a very expensive, it's very expensive, huge premium. There is very high capacity, but it's cost prohibitive. In these downtown cores, it's especially cost prohibitive because it means digging up downtown areas, closing off streets, very difficult from a permitting point of view. Wireless provides certainly the best value. It's a medium to high capacity, certainly not the unlimited capacity that a fiber provides, but still very well suited to meet the capacity growth requirements and trends that we're seeing. It does require radio planning for line of sight, for non-line of sight, for interference, so there's planning required. There is a need for some new products which are being introduced, DragonWave being one of those, introducing those for smaller antennas and microcell optimized products. CapEx and power have to be scaled down to be cost effective in a microcell network. So we've got to have a solution that meets the CapEx requirements and is much lower than a traditional macrocell deployment. So just a quick look at the wireless technologies for point-to-point backhaul and the reach capabilities. So if we look at the sub-6 gigahertz unlicensed bands, and the reason I mentioned these first is these are the ones that can be used for near and non-line of sight applications, which you will need some of these in an urban environment. When we look at an 80 meg worth of capacity, your range can be over 10 kilometers, so plenty of range. Even at 130 megs, still lots of range, 5 kilometers. This does, however, assume no interference and assumes line of sight, so you do reduce in reach or capacity if you move into an interference environment or into a blocked line of sight environment. Your capacities will reduce or your reach will reduce. Then moving to the licensed bands, the 24 to 58 gigahertz bands, you can see depending on the rain rate, the range can is well in excess of a kilometer, except for in 60 gigahertz, which will be anywhere from 0.3 to 0.9 kilometers. Your capacities are at 256 QAM, 350 megs and above, and a QPSK about 67 megs. So what we typically, in the planning studies we're looking at here, we'll typically focus on the 256 QAM modulations, and these reaches certainly fit well within those requirements. So looking at some of the target architectures that we would use in a small cell environment. The first architecture is a hub and spoke architecture, so very traditional. One of the limits here is there can be congestion at a hub site, so you'll have antenna loading at a hub site. For every connection, you're going to have an antenna, so you could have 5 or 6 antennas on a lamp pole, which is less desirable. You also may have some interference by everything focusing on that single point. So there is some downsides of doing a hub and spoke architecture. Also, you require line of sight to each end point if you're using line of sight architecture. I did a direct connection to each end point. You can do optional daisy chain spurs, which can obviously provide some additional coverage from this. There isn't path redundancy, so it does. You don't have an option for a high availability architecture. Looking at the ring architecture, your links are much more distributed throughout your network, so you don't have the same congestion at a hub site from both a antenna point of view or from a spectrum congestion point of view. You also have relaxed line of sight constraints because you can connect to an intermediate hop. You don't always require direct line of sight back to your hub site. You can also use optional spurs to extend your coverage, and you get built-in redundancy for your site, so you can have higher availability options. So we believe that you won't be able to use a ring everywhere, and you won't be able to use a hub and spoke everywhere. There will be a combination of both technologies. And then looking at line of sight versus non-line of sight. So line of sight above traffic level in urban areas gets routed along the streets. Typically, you zigzag across the streets so that you don't have blockage of your near site buildings. Your backhaul candidates are selected based on your line of sight. So sometimes what that means is you may end up selecting a site more for line of sight requirements than necessarily for optimal base station access requirements. So there are some trade-offs, certainly, depending on which solution you use for which site. Non-line of sight has a lower link capacity, also has a higher delay because it's a TDD type of system, and there are some self-interference and latency concerns. However, it does provide resilience to partial line of sight. It does provide more architecture options, allows you to connect to almost any site, and allows you to optimize your RAN site. So, there are pluses and minuses of both. The line of sight, because it's higher capacity, you can use more in a ring architecture or as an aggregation link for multiple access links off of it, whereas the non-line of sight, due to the low capacity and high latency, you typically can't use in a ring architecture or in a daisy chain and aggregation architecture. So we see a need for both types of technologies in a network, both line of sight and non-line of sight, and the best way to get maximum coverage is to use both. So just looking at, and this is leading up to a reference network design that we're going to do. So if we look at a couple of the different architectures and design options that I mentioned, there's a hub and spoke non-line of sight option where you use all unlicensed non-line of sight equipment, single hops to the macro site. So you're always trying to have a single hop back to the macro site. And you can see on the diagram on the left, there's some of the loop lines. So those are all direct connections back to the hub site. Moving to the hub and spoke line of sight option, you end up much more in a daisy chain back to your hub. So instead of some of those direct connections which are looped around back to the hub site, you daisy chain back to the hub site because the line of sight is not available. However, there is higher capacity that can enable this daisy chaining, so you're okay to put multiple links together in daisy chain. In this case of hub and spoke line of sight, we also, in our case study, deploy repeater sites in some cases when required in order to get back to a site. We are, in our case study, doing a maximum of 3 hops of this architecture in a daisy chain. Then we look at the ring hybrid case, which can use either non-line of sight or line of sight equipment. We use licensed on ring links for the capacity because there's multiple sites being carried on that, so we need licensed technology to get the high capacity. And we use licensed on spurs unless there's no line of sight available, in which case we would then use a non-line of sight. And we use a maximum 1 hop to the ring node. So these are kind of the three different architectures that we're going to be looking at when we map it across an actual city deployment. And so the sample deployment and case study we're going to go through today looked at a macrocell network in a downtown core today, which had 11 base stations, 2.6 sites per square mile. Total coverage of the distance between sites was on average 960 meters, and the capacity per base station was greater than 250 megs. We're taking that and scaling that up by about 8 times, so adding 76 new sites, moving it to 87 sites total, decreasing our distance between sites to now 350 meters on average. Still having the same capacity per site, but obviously way more capacity in the downtown core because we have 8 times as many sites. So we're moving from about 4 gigs to 28 gigs worth of capacity in that downtown core. And we're moving up to about 16 sites per square mile. So this is really what the small cell architecture. And we're going to look at from a backhaul point of view what we had to do as we moved from 11 to 87 sites to try and serve all of these locations. This is a diagram of what the network looks like. So the yellow pins were the existing 11 sites, and the bullseyes are the microcellular sites that are being added to this to fill in the coverage. As I mentioned, so there's a maximum of 3 microwave hops back to the macrocellular sites. We're trying to take the microsites back to the existing macrocellular sites, which already have backhaul and in most cases already have fiber. We're putting a limit of a maximum number of 10 sites per ring, as I mentioned, line of sight only. And we are using repeaters to close rings. If there are cases where line of sight is not available, we'll use an intermediate hop, which may not have a base station, so an intermediate site which doesn't have a base station, but is just used for backhaul to balance a link back to close a ring. So looking at 4 different architecture comparisons. So first, hub and spoke line of sight only. We had moved up to 76 target sites. We were able to hit 67 of those sites. 9 fell out, so we weren't able to hit 9 sites, and we needed 11 repeaters to be able to hit to be able to do this. The average link length was about 300 meters. The average capacity was 360 megs link capacity, and the average latency was about 0.27 milliseconds. When we look at the hub and spoke non-line of sight architecture, we ended up with we could hit 69 sites, so 7 sites weren't covered. No repeaters were needed, so we didn't need any intermediate sites in this case, whereas those were needed before for in the line of sight case. We have obviously significantly more antennas per macro site because it is a much more hub and spoke type architecture, so that's why we move up from 2.3 to 4.8 antennas per macro site. We have our link length increases because we are doing these direct links back to the hub site, so it goes up to 478 meters. Our link capacity goes down because of the technology, so down to 150 megs, and our average end-to-end one-way latency goes up quite a bit because of the TDD architecture, so it goes up to about 1.5 milliseconds. Then if we look at the third option, which is a hybrid hub and spoke line of sight and non-line of sight, we can reduce some of the repeater sites. We get to 71 sites hit total. Only 5 fall out, and there's 5 repeaters. The reason we can hit some more, at first you say, well, why would you be able to hit in a hybrid hit any more sites than you possibly could in a non-line of sight? The reason is because in a non-line of sight, you're limited that you can't daisy chain many sites, because if you do, you end up reducing your capacity per hop, and then it defeats the purpose of doing the small cell architecture to begin with, because you're sharing on a low capacity link. What you can do in a hybrid is you can have a high capacity link that can get you out further, and then you could have more non-line of sight links from that. And so that's why you can get further coverage by combining the two. So aggregating multiple non-line of sight links onto a high capacity line of sight link. So in this scenario, the link length is now in between the two, as would be expected. The average link capacity also is in between a pure line of sight and pure non-line of sight architecture, and the latency is in between as well at 0.7 milliseconds. The last one is the ring hybrid. So in the ring hybrid case, we were able to use to hit all of the target microcellular sites. We had 5 repeaters. We were able to have an average capacity of 290 megs. The average link length was about 340 meters, and the one-way latency was about 0.8 milliseconds. So the best coverage was in the ring hybrid case. The reason, again, for this is because we impose limitations on ourselves due to design limitations of how many unprotected links we can have in a row in an unprotected hub and spoke architecture. As I mentioned, there was a 3-hop limit. However, in a ring, you can have up to 10 hops in a ring and then have a hop off of that. So you can get much further from your target macro site to your target micro site using a ring and non-line of sight hybrid architecture. This just looks at the different diagrams of what the architectures look like. So the line of sight, in the line of sight case, you can see all the different connections. The red dots are the sites that we were not able to serve. So they're the sites that we couldn't get line of sight to. It's a little bit difficult, but there are some red triangles in there that are the repeater sites that are used in some cases where line of sight is not available to hop in between hops. If you look at the non-line of sight case, you can see there are longer hops, much more of a hub and spoke type architecture than the daisy-chained architecture that you move into in the line of sight case, and there aren't any repeaters in this case. Looking at the hybrid cases, so the hub and spoke hybrid, you can also see in this case there are significantly less repeaters. In this case, more sites are served. And then in the ring case, we serve all the sites, and primarily through rings with then some hops as access links off of the rings. We use some access spur links. So looking at the link distribution of the link length, you can see that reach isn't a huge concern. All of your link lengths, even in the non-line of sight case, are under 900 meters. In your line of sight case, they're all below 600 meters. So the technologies that we presented at the beginning, you may not remember them all, but they fit pretty well into this link length of range. So certainly, if you have 28, 38 gigahertz, you can easily get any of these link lengths with the line of sight technology. 60 gigahertz can typically deliver up to 300 to 400 meters, so you can usually hit about 90% of these sites with that technology as well. So, in summary of this, I think we see there's a huge need for greater capacity and indoor penetration spectral reuse, and this is what's driving the requirement to a small cell networks. There are significant challenges in small cell networks. I think everyone's still learning these because there aren't widely deployed field networks today, so we're all still learning what these challenges are. As we look, but I think it is well accepted that backhaul is one of the areas of one of the largest challenges and one of the biggest areas that needs to be solved. Certainly, our conclusion is doing a number of these studies is there are solutions to these, and that wireless backhaul can deliver high-capacity backhaul to the small cell architectures and small cell sites. That it will be a combination of technologies and topologies, so there will be a combination of non-line of sight, line of sight, repeaters, hub and spoke, multiple frequencies within line of sight, and rings. So there is going to be a wide set of topologies and technologies used. I don't think anyone's going to be able to use a holistic view of only rings or only line of sight or only non-line of sight. If you do, you'll end up making many trade-offs in terms of capacity and network performance to do that. So certainly we believe that a toolkit approach is what's needed to be able to hit the right amount of coverage and capacity and have a deployable small cell backhaul network. All right, great. Thank you very much. That really closes our case study on small cell backhaul architectures.
Okay, thank you, Greg, and for that, and Caroline as well. We have a number of questions about this exciting topic of small cells and backhaul, so I need to get right with those questions now. The first one from Elias is, I think, for Caroline, and that is, what is the rate of deployment between small cells and macro cells in North America versus Europe? Caroline?
Yeah, well, it's interesting. I think the first thing to point out is that the small cells that I think we're talking about today are not really being deployed currently. Of course, cells have been getting smaller, and you see a lot of pico cells being used for urban coverage in just standard 3G. But where you really start to change the architecture is by introducing very small cells, which, as Greg and I have been outlining, live at a lower level, often in different spectrum, and are generally highly integrated single sector cells, somewhat based on the femtocell idea that a lot of operators have used indoors. So most of those true small cells are still firmly in the building at the moment, and when they sort of come out into the public access network, some very early movers are doing that from this year, and they're mainly in Asia. We've seen Japan, Korea being hugely innovative in what they're doing with very small cell architectures of the kind that Greg was outlining there. As for North America versus Europe, it's there's not really a very common picture. We'll see certain operators moving early towards dense small cell networks certainly from next year, but it will be a kind of operator by operator case rather than a regional case. So for instance, in the US you see initially the LTE networks are being done very wide area, and companies like Verizon, they've still got a lot of big cells there. They're trying to get as much coverage as they can initially, and they also use other techniques like DAS, which are less popular in Europe. In Europe, the tendency with the operators will be to build out LTE initially as sort of urban hot zones, because they still have HSTA to fall back on for wide area coverage. So I think we'll see a more rapid acceleration of the use of very small cells, because they're very suited to those metro zone kind of rollouts. So I think the pattern of how those two regions will compare will not really be clearly seen for another couple of years yet, when we get to really big deployments as opposed to trials. And I expect it to be an operator-by-operator case. But I think both the regions, any operator that has significant urban territories to cover and significant rising data demands, which clearly is true of most of them, is certainly planning small cell rollouts. My feeling is that we'll see a quicker move in the HSPA community than the CDMA community, partly because of where the technologies come from.
Okay, thank you, Caroline. Greg, I have a number of questions for you now, some of them a little bit technical about your slides. And back on maybe around slide 4 or 5 there, you were talking about expanding network using microcellular. You started talking about the urban environment and the number of locations, the light pole locations and so forth. And yeah, and the question is, did the number 320 include all poles, including municipalities? They have, utility poles and such. And also, did it include municipalities, utility poles, and can those poles handle the loading of a typical Pico remote radio head?
Yeah, in this case, it did include. We did look at all poles in this location. Now, there's going to be obviously different sets depending on which city, but in this city, we did look at all poles, and we did look at suitability for the technologies we were going to deploy, which are fairly low weight, minimum loading type technologies. But certainly, the lower your weight and that your solution can be in terms of size and weight, the more pole options you have. And so we have a lot of focus at DragonWave for our technologies to minimize the weight and the wind loading.
Okay. Quite a few questions, Greg, so I'm going to move along here. The non-line of sight analysis, does that assume MIMO 2x2 or single input, single output?
So we had assumed a MIMO 2x2 for this.
Okay. Next question is from Rodrigo, and I'll just read it out. Now that we're backhauling using microwave radio, considering that a really good option, how does the capacity requirements in the future will probably increase? What is your opinion for microwave backhaul, and will this only be a rural option?
We definitely think that this is an urban option, and certainly this study was based on urban, and it was delivering well over 100 megs per site. So we certainly believe it's a urban option. It is why a lot of these architectures had limitations in terms of how many non-line of sight links you could do because of the capacity requirements to scale. Even how many line of sight links could be on a ring. That's why there are reach limitations, because we had to be at high order modulation. So we certainly believe that this does scale, and this meets the requirements per site. We are introducing, as a microwave vendor, we are introducing new technologies to improve that capacity. We have recently announced 2048 QAM, so high order modulations, multi-channel support, wider channels, and compression, which aren't included in this study, but are things that are important to help scale the network in the future.
Okay. Kind of a follow-up to that, Haig has a question here. He's assuming small cells have a peak busy hour traffic of about 30 to 40 megabits per second. That's what he's assuming. So he's asking, is there really a need for 300 megabits per second as you presented in your study?
Yeah, so again, we're more engineering to 100 megs per site. The 300 to 400 megs is the link capacity, and in the line of sight cases, we're daisy chaining, so we're putting multiple sites onto a single link because we're doing aggregation. So the 300 megs is not per site; that's a per link, which has multiple sites aggregated onto that link. That's why we can use the non-line of sight. If we had a 300 megs per site, that would eliminate any non-line of sight technology at all to be used. So our target is as 100 megs. I think 30 to 40 certainly is a very reasonable near-term environment, but we're definitely here in this study looking at something more scalable to meet the next few years of capacity requirements.
Okay, I'd like to remind the audience, everyone, that this presentation will be available later this week, maybe Thursday or Friday. So any questions that are not answered can be followed up with the presenters by email. Moving on, considering there's a push in the United States now for broadband and alternative structures, this question, Greg, is from Don, and although light poles would be a logical structure to use, how about rooftops with the advantage of having AC power readily available, perhaps? Specifically, his question is, don't you think that the carriers would still have to fall back on rooftops versus pole after pole?
Yeah, so certainly I think where rooftop is available is great. Rooftops are typically privately owned, and therefore the owners look at them as revenue opportunities. Most poles are regulated, and the FCC has put a very low cost to get access to those that they've regulated, of which about 30, I think, of the states have adopted those regulations so far. So the poles are one a lower cost option. You can talk to typically one person to get sites everywhere, whereas getting building access, even in a macro environment, is very difficult in talking and negotiating leases with every single owner for a building. That's something right now that already cripples cellular deployments in a macro environment. When you try and increase the number of sites you're doing by 8 or 10 times, it would really hinder your deployment. That said, that is certainly the desired location. But I think it's DragonWave and certainly the customers and carriers we've talked to don't believe that it will be feasible that they can get the number of sites and leases that they require if they limit themselves to building locations.
Okay, thanks. Another maybe kind of installation or implementation question, one from Senkar and one from Kevin, about the power required for these for your solution, the type of solution you offer. How much DC power is required, or AC, or whatever, and also battery backup. Is that something that's available?
Yeah.
Yeah.
So it depends, a lot of, we're getting a bit more into kind of the product, a bit away from here, from the case study, but our products can, depending on the architecture that you have, from a minimal architecture would be about 50 watts for backhaul, to more of a hub site with a switch could be more 300 or 400 watts. And then, there would be whatever the base station requires, which the base stations range from below 100 watts to 300 watts, depending on the type of base station that you're using.
Okay, let's see. How about this question here? Caroline, I'll ask this one to you and see if it's you want to take this question or pass it on. Do you perceive a shift in operators' CapEx or OpEx spending towards backhaul with the rise of small cells, and are the operators prepared for that?
Yeah, I mean, definitely. There's a gap between theory and reality, as I guess there often is. But when we look at the cases and the way that networks are needing to be built, you can see that there needs to be a shift towards backhaul. But some of the operators are resisting that. It tends to be, it's quite a typical scenario probably, but there tends to be quite a high awareness among people who are actually planning the network that massive increases in backhaul capacity are going to be required. And although backhaul technology is getting cheaper, operators also want a lot more value from them. They don't just want a dumb link, they want intelligence built in. And so they want sort of a product that contributes to the performance of the whole network. So that is carrying a higher value, and that requires a shift. However, at the kind of maybe the financial, more strategic area of the operators, there is still a perception, not in all cases, but in some cases, that backhaul should be cheap, shouldn't be a large part of the proposition. So yes, there are a lot of internal debates and disputes, but we think the overall trend will be that as a percentage, backhaul will take up more, certainly more CapEx going forward, not necessarily more on the OpEx side, because there's an awful lot of work being done on making backhaul much more affordable to manage and so on an ongoing basis. And the integration of backhaul with access network is important from the OpEx side, which we are seeing as a key trend in small cells, because of course that does have a big impact on OpEx in terms of cell sites and general support and maintenance, and as well as on upfront CapEx. So yes, we do think there's a shift. We think there's some resistance to it. Every part of the network is having to be very price competitive, but we think in 3 years' time we'll see that the percentage allocated in the budget to backhaul will have increased in almost all operators as a percentage.
Yeah, okay, Caroline, and just maybe a follow-up, we're talking about LTE and backhaul. How about LTE advanced? Is there any projected additional requirements or changes in the backhaul patterns on the horizon for LTE advanced?
We see the changes as being less dramatic in architectural senses, but we do see that at the LTE advanced stage there will be a much accelerated move towards these very dense networks of small cells. a lot more of the organization of the small cells is included into the default standard at the LTE-A stage. So there'll be a lot of operators that hesitate to do it at LTE who feel the technology at the minute is not proven enough, who wait till they get to LTE Advanced before doing serious small cell deployment. So I think it's not so much that there'll be a huge architectural shift at that point, but there will be a kind of intensification of the market, and it will become somewhat easier to do it, partly because there'll be more experience in the market, but partly because more elements of a successful small cell network will have been standardized by that point.
Okay, thanks. Thanks, Caroline. And Greg, I'm going to ask you a little bit about frequency bands, maybe a two-part question. One is about the 80 gigahertz. Is that band being considered for picocell backhaul? And also, as a corollary, what frequency band do you think is most appropriate for line of sight? I believe they say line of sight hybrid ring architecture.
Yeah, so the 80 gigahertz, although it could be a suitable band, right now there's limitations on minimum antenna size, which are limited to 1 foot minimum antenna size, which we think is too large for microcell deployment and for lamp pole mounting. So all of our architectures are designed around more technologies and bands that can use 0.5 foot antennas, so like 5-inch antennas, less than half a foot antennas for that small cell deployment. So we don't see 80 gigahertz right now. There is discussion around changing the regulations, and if that happens, it could become a potential technology at that point. In terms of frequency bands, we think that all the bands we've laid out are suitable bands, 24, 28, 38, and 58. However, it depends a lot on where you're deploying and what country you're in and what spectrum's available in the country, what the cost is to license the spectrum, who owns it, and that varies a lot by country. In the U.S., 24, 28, and 38 are owned by spectrum holders, but generally can be leased. There isn't a lot of deployments that have happened today in those bands, so they're pretty available at pretty reasonable cost. So they're good options that provide good reach and good availability. 58 is also available in the U.S. So in the U.S., really, you've got 4 kind of suitable options. In other regions, it really depends on the country. In Europe, there's a lot of places where 38 is quite available. And 58 is also becoming quite available throughout Europe.
Okay, next question. Can Greg describe the multipath in the urban line of sight microwave links case that they had to cope with, referring to the delay spread value? I don't remember that one. Maybe you do. Do you remember that?
No, what I could say is in the non-line of sight, you're absolutely right. We did not this isn't a past actual deployment. So the non-line of sight cases, we've assumed best case for the non-line of sight. We've assumed that in a blocked path, we could still, if it was within our range, we could still connect. In reality, when you get to the field in a non-line of sight case, there may be cases where you aren't able to bounce around the obstruction, and perhaps you can't connect in the non-line of sight. So there are cases there where the non-line of sight paths that you think you may be able to get may not always be available to you. But that level of granularity can't be determined through a planning tool. You really have to determine that through your field deployment.
Okay, Greg. Do the cost and deployment models work in Canada, where Industry Canada licensed microwave fees are based on capacity per licensed link? From Pat. They're asking about Canada and the models. Do they work there, where the microwave fees are based on the capacity per link?
Yeah, so certainly in a Canada case, you do want to have more direct links, as many direct links as possible, because you do pay, as you say, on a per megabit per link. So there are In some cases, it can be more expensive from a licensing point of view to do a ring architecture unless you're in some of the higher bands where it's more cost-effective, 38 where it's more cost-effective. But certainly, you are right. The more high-capacity links you have in Canada, the more you pay. This hasn't been mapped across an economics per region, so you would have to do an economic optimization per region and per licensing environment, as well as your tower and mounting environment for each region to have an optimal economic solution for each region.
Okay, next question from Neil. Will carriers outsource the wireless backhaul management? Neil claims he's asking, is this a trend in the market?
Yeah, I'm not quite sure if it's a trend. It's certainly something we've seen for quite a while. That has, I'd say, peaks and valleys, goes up and down. We certainly do see that it happening. However, at the same time, we recently saw some significant issues with fiber tower, that's what their business model was. So, although there is some outsourcing that's happening, I think it varies a lot depending on the carrier. Doing it in microcell is going to be more difficult than doing it in macrocell for the reasons that Carolyn mentioned, that there's going to be a lot of integration between the backhaul and the radio access layer itself. In many cases, they'll be part of the same unit. That makes it very difficult to outsource backhaul if the carrier-owned base station is part of that backhaul. So there's not a clear demarcation point anymore, like there is if you lease backhaul in a macro case. So it will be more difficult to do that unless you do an entire lease and you lease out your RAN or do a RAN sharing type case. It will be much more difficult to outsource just your backhaul in a macrocell environment, in a microcell environment, sorry.
Okay, just a few more here, and we'll wrap up here in a few more minutes. Just a reminder, the presentation slides will be available in a couple of days. Contact information for Greg, Caroline will be at the end of that presentation. I'm going to ask this one to Caroline, and it is, Caroline, what are the implications of the cloud RAN trend for backhaul?
Yes, that's an interesting one. It's a little further out, but there are several operators who are interested in running all the sort of operations of the network on a central server, which will then feed a lot of cells. They don't have to be small, but they will be in many cases. And China Mobile's been the leader of this particular trend. They are claiming you need fiber, through and through to have the reliability to centralize everything, have everything virtualized on the server. However, we're already starting to see both operators and suppliers who are doing tests. They're in labs at the minute where they're using wireless to get the same effect but with slightly lower cost. So I think it's another opportunity. I think it's not an architecture that all operators will adopt, but it will have its place, particularly among the very big providers, and particularly we're seeing this in the East Asian economies, a big interest in this. However, the big obstacle, if China Mobile proves right, would be that if you have to have fibre at more or less every site, then that will be impractical for many carriers. China Mobile's in rather a rare position. So we think over the next couple of years a wireless solution for that will develop with suitable capacity and reliability to support Cloud RAN. And as I say, for a vendor that gets into that market, I think it will be quite a significant opportunity because these will be very big rollouts where they can't.
Okay, thank you, Caroline. Greg, just one or two more here. William has a question about directional antennas. Perhaps he means smart antennas or something like that. Can directional antennas in the backhaul provide better link bandwidth?
Yeah, I'm not quite sure I fully understand. Certainly our antennas that we use are fairly tight beam, but they are, especially especially in the 28 to 60 gigahertz. They are directional. They're typically small parabolic, about 3 to 5 degree beam width. That is what we use to have the high capacities that we need, as well as the good gains needed for these bands.
Okay. Next question is, do you have any recommendations on network planning tools for this type of design? And did you use 802.11n as in Nancy at 5.8?
The 5.8 we used wasn't an 802.11 solution. It's a proprietary implementation. DragonWave has a product called the S series, which we used for that. For planning tools, we use a combination of tools. We some of the traditional RF planning tools, and then we also use Google Earth for to get a view of where line of sight's available in a metro area, as well as some SRTM data for building topologies.
Okay, let's see, one more. We're about to wrap up here. Which role can play in the future of the satellite backhaul for small cells? Any comments on satellite backhaul?
I think the satellite backhaul is fairly limited in terms of capacity, especially on the uplink. So we don't see it being really suitable in this type of environment. I think in some kind of rural environments where you don't have you have no other option, it can be suitable, but not for a high capacity urban environment.
Okay, one more question. In your slides, there was an asterisk on the ring hybrid example. An asterisk. I'm not sure which slide that was. Do you recall that, Greg? On the ring hybrid example, you had an asterisk, and Edward is asking what was the reason for that. Maybe, yeah. If you don't see it, then Edward, you can follow up by email sometime later.
Yeah, I'll have to follow up offline on that. Yeah.
Okay. Okay, let's see. I'm just trying to, some of these are the same questions. Here, one more from Neil. Are you seeing a widespread acceptance by utility companies and municipalities to allow the mounting of equipment on pole assets? Certainly there are growing, there's firms out there that have their own utility companies, and they're able to deploy these more effectively, but not everybody is a utility and a wireless company. Your thoughts on that, Greg?
Yeah, I think there is some. It's still very early in the microcell area, so yeah, I would say to call it a trend yet would be early. It seems they're willing to cooperate, but I'd say it's still early to really have a view as to how well of an uptake we'll get from them.
Okay. All right. Well, we're going to call it quits for now. Still have a few questions on there. Apologize we can't get to all of them, but again, this presentation will be available online. You'll get an email in a couple of days, let you know where to go to look at it, and you can also follow up with Greg and Caroline on the further questions. So any last words from Greg or Caroline before I close this out?
Just thank you for the time, and just to reiterate, as you said, if any additional open questions you've got, feel free to contact us offline via email, and we'll respond to the questions. And appreciate the time from everyone.
Yeah, similarly, thank you very much for listening, and do feel free to contact me by email for any follow-up.
And again, thank you, Greg. It was a lot of information, but a good overview of DragonWave's product, and also some good information there to guide us in backhaul for small cells, which is coming to us now and in the future. And also, Caroline, for your insight into backhaul and small cells as well. And we look forward to hearing from you all in the future. And thank everyone for joining us today on this Wireless Communications Association International webinar, and please look forward to additional webinars going forward in the exciting world of wireless. Everyone have a good afternoon, good evening. Thank you.